So in the last lesson, we talked about forces, we talked about Newton's laws, how forces work. In this lesson, we're going to look at a specific type of force. And the specific type of force we're going to look at is the force caused by friction. So friction is a contact force that's created whenever two surfaces move together. One easy way we're all pretty familiar with friction, but if you want to think about friction, rub your hands together. You feel your hands get warm, you hear the sound. The warmth is caused by friction. The sound is caused by friction. It's energy being dissipated due to friction. Okay, so friction is caused by two forces that rub together. And it could be any two surfaces that rub together. It's caused by irregularities or roughness in the two surfaces. So if you have metal parts on contact with each other, the more pitted the metal becomes, the rougher the surface, the greater the amount of friction. So wear on parts can increase friction, which can then increase the heat that is experienced due to friction and lead to potentially catastrophic failure in a piece of mechanical equipment. One important thing to note about friction is it's always opposite the motion of the object. So if an object is moving forward, friction will be backwards. If you're pulling an object left, friction will be right. It's always going to be in the opposite direction of the force that is causing the object to move. Now, how do you calculate friction? The formula we're going to use to calculate friction is shown down below. So this is the formula we're going to use to calculate friction. We say FF, force of friction, it's just a way of labeling what that force is to keep organized, is equal to this funny little U shape is called mu. It's a Greek letter, and it is the coefficient of friction. It's a factor of, it describes how rough the surface is. So it's the ratio between the force of friction and the force between the object and the surface that describes how rough it is. The larger this value, the greater the force of friction you will have. The smaller that value, the lower the force of friction. And then Fn, this is not net force, it's normal force. Now I will often write F little n as well. So you'll see F big N or F little n. Doesn't really matter which letter you use. And we use that to denote normal force. Now normal means perpendicular. We often think of normal as normal and abnormal. If I said something was normal, you'd say, well, that's something you'd expect every day. But in math terms and in physics terms, the word normal means perpendicular. So perpendicular means up at 90 degrees to the surface. So if the surface is horizontal, normal force will be straight up. Now we're only going to work with horizontal surfaces. I'm not going to get into surfaces on angles with you folks, just because that's an added complication that we don't really have enough time for. And if you understand the other pieces, it wouldn't be hard for you to extend and apply in that scenario anyway. So what types of friction are there? There's two types of friction. We're just going to discuss the two types, but we won't actually really do a whole lot with them. We'll just look at friction in general, but the two types of friction is static friction. So static friction is on a stationary object. So this is the friction that exists when there's no motion. So if I if I push back in my chair, I can apply a force on the floor, pushing back on my chair, that doesn't actually move the chair. If I stop at just the right spot, I can feel there's tension in my legs that are pushing, but the chair isn't moving. Static friction is the type of friction that keeps my chair from moving because I don't have quite enough force to be larger than it. Once I apply enough force to be bigger than static friction, my chair rolls backwards. When my chair is moving, we call that kinetic friction. So kinetic always has to do with motion. Static friction is always bigger than kinetic friction, which means once an object starts moving, it's easier to keep it moving. So in your experience, I always like these think and apply questions. In your experience, which requires less pushing force, to get an object to start moving or to keep it moving? I know lots of times, especially if it's something that's heavy, you know how you do the run and push in, and then once it starts moving, you can keep it going? That's an example of static friction, keeping it from moving at the start. So you put that extra force in to start it moving. And then once it starts going, you can relax a little bit because the kinetic friction is a little bit less. So in motors, that's often one of the same things. In order to start, let's say we're starting a fan moving. In order to get that fan to start moving, a little bit of extra load is required. A little extra force for the motor. So there's a little more load on the motor at the beginning, but once it starts moving, instead of having static friction in the fan, you would have kinetic friction in the fan, so there's less load. And sometimes we will see that if you were looking at a chart and you were looking at amperage, you might see when something starts, there's a peak in amperage and then it decreases. I say amperage because you often look at load on electric components. And the more amps that are required, that always means the more load there is on the system. So that's something that I know I've often seen it at the plant where my husband works. I used to go into Cavendish quite often when he was first in his trade, because I had the chemistry background that he didn't have, and they allowed visitors, and I'd go in and he'd explain the process to me and I'd explain the process from a chemical perspective to him. And it was a chance for both of us to learn. And one of the things that I remember often seeing was he'd look for these amperage peaks, and that would tell him when there was too much load on a motor. So if you have the ability to connect to an instrument that will measure how much current is on an object, you can use amperage as a means of watching force. And whenever you get these big spikes, a really good thing to think of is it caused by friction? What's causing the extra load? All right, so we're going to do a few examples of calculating friction just using our simple equations. This is mostly going to be about drawing free body diagrams. We're going to be calculating weight or the force due to gravity, and then we're going to look at calculating what the normal force is. We're going to look at some standard examples, then we're going to look at a couple of scenarios that use what we call vectors. And I know I haven't talked about vectors too much with you, but they're really easy. And I know you folks all understand how to calculate your trig. That's been proven to me, so you'll be able to apply it. The first examples we're going to look at, we don't have to worry about any angles. So what we're going to start with, we'll read the question and we're going to draw a diagram that matches. A 3.75 kg block is pushed along a tabletop with a force of 45 newtons. The coefficient of friction is 0.65. You'll notice there's no units on that. I want you to A, find the force of friction, and B, find the acceleration of the block. So first thing I always start with is a free body diagram. And we talked about free body diagrams earlier when we were looking at forces. So I draw a free body diagram. I always start with a box because that allows me, it's just an information controlling. You could draw a dot if you wanted. Some of you may have done dots, but I like to be able to put my kilograms in the middle. I like having space to work around it. All right, what forces, so this is on a tabletop. So here's my surface. What forces are acting on it? Well, it says it's pushed with 45 newtons. So I'm going to assume it's pushed forward. And it's 45 newtons, and then we'll say that's our applied force. Okay, so that's the amount of force I can push with. Friction always is opposite motion. So friction is going to be in the other direction. And we'll just label it, we don't know how big it is, but we're just going to label it as force of friction Ff. There's two other forces we know that are going to be important to each other. We have the force due to gravity, which is downward. The force due to gravity is equal to m times g, which we can calculate. Our mass of this block is 3.75 kgs. The acceleration due to gravity, or g, is 9.81 meters per second squared. Multiplying those two values together, you will get a force of gravity that is 36.8 newtons. But we're missing one force that we need to calculate friction. We're missing normal force. Now, normal force is perpendicular to the surface, and it's the supporting force. Remember, Newton's third law says that for every force there's an equal and opposite reaction. Well, in order for this box or block, whatever object it is, to sit on the surface, it puts a pressure down on the surface. but there has to be a balancing force in the other direction to keep it from accelerating in the vertical direction. So that force is called the normal force. And in this case, it's equal and opposite of gravity. Why is it equal and opposite gravity? Well, there's no other up and down forces. So the only way to balance them out is for it to equal gravity. By the end of the lesson, you'll have found a couple examples where the normal force will not equal gravity, but gravity will still come into play with it. You'll just have a little adjusting to do. So this is our full diagram. We have all of the forces that we know information about. Now we're going to go back to our question and see how can we use these to find the information that we need. So I'm going to start with A. Find the force of friction. Well, we just found that the force of friction is equal to the coefficient of friction times the normal force, or the force between the object and the surface. You can think of it as how hard the surface pushes up on the object. Okay? So in order to calculate this, we have to find the information in our question. This value is equal to U, and then we have our normal force up here. Now, we had to find gravity just so we could get the normal force. So you find there's a lot of extra calculations in this that you have to do. So you have to find lots of other information just to answer the simple question. So you'll feel like there's more calculations in this, especially if you're not used to doing physics questions. So the first thing we do is we take our coefficient of friction, which was 0.65, and we're going to multiply it by the normal force, which is 36.8 newtons. What do we get for the force of friction? Well, the force of friction happens to be 23.9 newtons. And you'll see our diagram is a really good collection of all the information that we need. So now let's go back and we're going to put that into our diagram because it's going to help us with visualization. I'm not sure I have, it must be something to do with my tablet putting pressure on, where I get these extra screens that pop up sometimes. So we have 23.9 newtons by friction, 45 newtons by the force applied. So we've done our first question. We found the force of friction. For B, I want to find acceleration. Well, how do I find acceleration? Well, Newton's second law told us that the net force, the overall force on an object, is related to the object's mass times its acceleration. So that's the formula we're going to use, where we have the net force. So positive forces minus negative forces, you can think of it that way. It's tax time of year. You have what you make minus the deductions gives you your net. So you're always subtracting two things to find your net force. So we're thinking about combining these forces together. One's in the forward direction, one's in the reverse direction. So you can think of one as positive and one as negative. So we need to find the F net. What is F net? Well, in this case, let's say 45 newtons is positive. So we have 45 newtons forward minus the force caused by friction. So that takes away from my applied force. And that will give me a net force of 21.1 newtons. Now we can find out, go back to this equation and find out our acceleration. So we start out with 21.1 newtons is equal to, we know the mass is 3.75 times the acceleration. Simple rearranging, divide both sides by 3.75. Cancels and we get acceleration is equal to 21.1 divided by 3.75, which is 5.63 meters per second squared. Well, those are the units that you always have for acceleration. Okay, so the acceleration is the result of whatever force is left over after I've overcome friction, whatever the extra is causes the acceleration, and that's your net force. So drawing the diagram can really help with just solving some of those math components. I strongly advise it. In fact, for your assessment, it will be a required component for your grade. In SAM, I can't enforce it. So you have a little bit of freedom in your quiz, but if you're not getting your quiz questions correct, stop and take some time and sketch your diagram. If you make the diagram the first time, you probably won't have to do it the second time. Let's do another example. A 0.2 kg puck is pushed across a sheet of ice with a force of 0.240 newtons. If it moves at a constant velocity, find the coefficient of friction. Now, there's a couple words that when you read a question like this kind of should jump out to you. When you see the term constant velocity, you should have some alarm bells go off. Now, this is my third time teaching this section this year. So if I forget to tell you something, I apologize in advance. Sometimes by the time you've gone through it 3 times, I've done it once in the hardcore physics version. I've done it once in the physics light that Otto does, and now I've got it for you folks, for you're getting kind of the light summary as well. So hopefully I don't miss anything. So if an object moves at constant velocity, Newton's first law tells us that an object moving at constant velocity, so its motion isn't changing, the velocity is not changing, will have a net force of 0. So constant velocity, when you see that, I want you to think F net equals 0, and that's Newton's first law. Okay? So that's going to help us out. So first we're going to draw a diagram and we're going to think about this principle, and using this principle, we're going to be able to solve the problem. So here's my puck. Again, everything I draw is a box. I used to think I did several art classes, but I'm still quite glad that in physics, I can get away with boxes and dots. I'm not exactly the best artist, especially sketching on a computer. My sister would probably dazzle you with great designs, but she couldn't do physics. So I guess you're just stuck with me. So we have a 2 kg puck, 0.2 kg puck rather. It's pushed across the ice. So we'll say that's the force there. 0.240 newtons is the force applied. And we'll draw our surface just so we're reminded that it's there. Gravity is going to pull down. It's always there. If it's on a surface, there's always something balancing gravity. That's our normal force. And the question says friction, so we know there's friction and it's going to be opposite of my push. Okay. Now let's think about what we know. Net force equals 0 because velocity is constant. So in order to, that means the forces are balanced. Okay, if the forces are balanced, my applied force, the force I push with, must be equal to the force of friction. So we would have 0.240 newtons. Now you can probably see how that helps us with our question. If we know the force of friction, we can find our coefficient because the force of friction is equal to the coefficient of friction times the normal force. And we can find this. We can find the force of, we can find this using gravity. And that will leave us with just one thing that we don't know. So let's go through and we'll calculate 0.200 times the acceleration due to gravity, which is 9.81, will leave us with a force of friction or a force of gravity that is 1.962. Now I've kept some extra decimals in here. You'll notice there's 3 digits after the decimal in each of these questions. So keep at least 3 digits, kind of match it. And that will make sure that when you get your final answer, you're able to round to have things work out. Sam's going to be a little fussy on rounding. And if you think rounding is what's caused an error, please reach out to me and let me know, and I'll take a look and do adjustments if needed. Now, if gravity is pulling downwards on the ice with 1.962 newtons and it's balanced, that means the normal force is 1.962 newtons. Okay, because there's no other forces on it that are up or down. So now we come back to our equation and we substitute. 0.240 newtons is the force of friction, is equal to the coefficient of friction times our normal force of 1.962 newtons. Rearranging it, divide by 1.962. And you'll see when we're dividing normal force and we're dividing force of friction by normal force. That's why the units cancel on mu. So the coefficient of friction is going to be equal to 0.122, and there's no units. And I've rounded to 3 decimal places because there's 3 decimal places everywhere else. And that's our final answer. So not overly complicated. They do require you to think a little bit. They require you to really draw these diagrams to think about balancing. There's some hidden information sometimes, so you have to kind of stop and process. But that word constant velocity will be your clue that the forces are all balance each other. If you see the word acceleration, you know one's bigger than the other. All right, let's go on to a third example. Now this example really takes some thinking. It's an easy question, but it does require some thought. A 1.1 kilogram textbook is held against a vertical wall with a force of 45 newtons. What's the coefficient of friction between the book and the wall? So it's like if you've taken the book and you're just holding it like so, pushing against the wall, okay? The book's not sliding up or down, it's just being held into place. It could be any heavy object you're pushing on a wall. Let's say you're mounting a heat pump and you're holding the heat pump, holding things up into the wall so somebody can align templates. Just a heavier version of the textbook, that's all. The rougher the wall, will it be easier to keep it up or will you have to push harder to keep it up? That's kind of what we're thinking about in this scenario. So the first thing I'm going to do is I'm going to draw a picture. So here's my wall and here's the book. I am pushing on that book with 45 newtons. And that's my force applied. How much is the wall pushing back on me? The wall pushes back with 45 newtons. If the wall is pushing back with 45 newtons and it's perpendicular to the surface, this is my normal force. Okay? Now, what force is friction fighting? If this book was going to move, what would cause it to move? Well, in this case, what would cause it to move would be gravity, would pull it down, which means the force of friction must be up. Because it can't go into the wall, and friction is for sliding along a surface, so it has to be in the vertical direction. That's kind of where this question makes you think a little harder. So what is the force due to gravity? Well, the force due to gravity is going to be 1.1 times 9.81. And that leaves us with 10.8 newtons. Now, if this book is not moving, what do we know about the forces? The forces must be balanced. So our friction force must be 10.8. So if we have no motion, that equals balanced forces. The last example, it was moving at the same motion, the constant velocity, and that was the forces balanced. This time, we still have Newton's first law that says if there's no motion, the forces are balanced. All right, now let's figure out what do we need to find the coefficient of friction. Well, just write your friction formula. Force of friction is equal to the mu, the coefficient of friction, times the normal force. And then go back to our diagram and substitute in what you know. Well, we knew the force of friction was 10.8 because it balances gravity. Equals the coefficient of friction. The normal force balanced my push into the wall because the wall pushed back on me. And now we divide both sides by 45. And if you do that, you will get the coefficient of friction is equal to 0.24. I've used 2 decimal places because there were 2 digits, 1.1, a 4 and a 5 in each of the given numbers. So that gives me a good example of where to round to. Those are the 3 simple examples of calculating with the force of friction. Now, things to remember about normal force. This is going to help us for the next 2 examples, which are going to be a little bit more complicated. First of all, normal force is not always equal to weight. You had one example of that already. When you pushed into the wall, normal force pushed back on you equal to the push you pushed into the wall with. It wasn't in the same direction same plane as gravity. So you've already seen one example of that. So it's often equal to gravity, but not always. Draw a diagram to prove it. It's always going to be perpendicular to the surface. So perpendicular, think of that upside down T shape. Or it could be like this. Okay? Always perpendicular to the surface. It will always balance the force applied to the surface every time. It's going to balance out the forces applied to the surface. Now we're going to see some examples now where we're going to have to think about how big would the normal force have to be in order to make this balanced. Now to find the normal force, we're going to diagram all the forces perpendicular to the surface. This use vectors if necessary. I'm going to explain that. Okay, so this is coming up. That seems like Greek right now. That's coming up and it's going to be really easy. It's just trig. And then you'll balance the force so that F net is 0 in the vertical direction. I should have maybe clarify with that. I'll say vertical because usually we're dealing with vertical, but in the direction of the surface. The book is the only kind of example that we have where we're not dealing with a vertical surface. All right, I want you to think and apply for a minute. This will let me grab a sip of tea since my voice gets croaky when I record too many things in a day. If you pull with the same force across a rough surface, I should have pull or push, which scenario would result in a greater acceleration? So in other words, I want you to think about where is there less friction? Okay, where is there less friction? Because if there's more acceleration happening, that must mean the force of friction was smaller. So let's analyze it for a second. Hopefully you have an answer or a prediction. It's okay if it's wrong. It's okay if it's right, even better. In this case, we're pulling upwards on the ice block, or it could be a crate, any object. If you're pulling up on an object, will you reduce the friction or will you increase the friction? Let's think about what happens. So we have this object, we're pulling, and part of our force, so we're pulling at an angle, part of our force is upwards. Force of gravity is downwards. Now it's still on the surface, so we know these two aren't balanced. So we also have to have normal force pushing up on the surface too. How would we figure out how big our normal force is? Well, the normal force has to balance out what's left over of gravity after I take into account the amount that I'm pulling upwards. I used to often do an example in the class because I had an extra desk. And I would say, would it be easier to push this desk if I'm pushing down or if I lift it a little bit and pull? And the answer is always if you lift it a little and pull. And this is why. Our normal force is going to be equal to whatever's left from the force of gravity after we take off the amount that we've lifted up already. So we're already counteracting a little bit. So the normal force here is smaller than gravity. So that should reduce friction. Because we have a smaller normal force. Normal force is smaller than gravity, so it's going to reduce friction. Let's look at this scenario. In this scenario, I'm pushing down. So some of my applied force is downward. Gravity equal to the weight of the object is also pushing down. The normal force up has to be much larger. The normal force has to support the force of gravity plus my downward push. So the surface is pushing up a lot more, which means an increase in friction. An increase in friction because we have larger normal force. We have a larger force, larger normal force, a larger push from the surface up on the object. Hopefully that makes, if that doesn't make sense to you, I want you to find an object in your house or in the classroom, an object somewheres, and I want you to test it. Simple as sliding a table. Try pulling it at an angle and feeling what that pull feels like. Then try pushing downwards. Now, sometimes just based on our bodies, one feels easier than the other, but based on pure physics and the forces, not thinking about is it an awkward motion or not, you will always have, my pen's here, you will always have a less friction if you pull upwards a little bit than if you push downwards a little bit. And that's just really simple logic for, well, how can I improve or make it easier to move a heavy object? You guys are going to be moving some heavy objects, guaranteed. If you forget you don't have a dolly around with something that can be slid across the floor, there's some strategy physics gives us that we can engage that helps us move things. So now we're going to do two examples that are based on the images you just saw. The only thing that's going to change is our angle. So in this example, a 215 kilogram crate is pulled with a force of 2,400 newtons at an angle 15 degrees upwards from horizontal. Before we go any further, what I'm going to tell you to do is stop now and draw the diagram. So we're going to do that, and then we're going to look at what we have to calculate. So let's get a picture of what's happening first. So I've got my crate. And I'm pulling it at an angle, well, I guess maybe I'll draw somewhat to scale. I think my box is crooked because my tablet's sitting crooked on my, oops, I don't want a pointer, I want a pen. All right, so we'll go 15 degrees. It's not quite 15 degrees. Okay, draw a triangle. We'll see why I draw this triangle in a sec. So we'll say that's 15 degrees, even though it's probably not. And we're gonna say my pull is 2,400 newtons. Okay, so that's our picture. Now that we have that picture, let's finish off our question. We'll see what it is that we need to figure out. So the first thing is, A, what's the normal force? What's if the coefficient of friction is 0.91, what's the net force? And then what's the acceleration? So first of all, we need to find the normal force. Well, let's think of all the easy forces that we could figure out. And there's one force that's a nice, easy force to figure out. The easy force to figure out is the force of gravity. If in doubt, always calculate it first. So 215 kilograms times 9.81 meters per second squared leaves us with a force of gravity equal to 2,109 newtons. Okay, let's diagram the other forces that we know. We know that there is a force pushing in the opposite of my motion. This is the friction force, but we don't have enough information to calculate it yet because we need to know what is the normal force. Now, I told you a minute ago that if you're pulling upwards on a box, the normal force will be smaller than the force of gravity because you're doing some of that upward pull. Well, how much of your pull is upwards? This is where vectors come into play. Now, I mentioned the word vectors earlier, and I said that vectors are when a measurement has a direction. Would you agree that a pull has a direction? It definitely does. It controls the direction something moves, so it has direction. We call it a vector. In this case, you'll see this triangle that I've drawn. Some of my force, I'll call it force applied, is up. Some of my force applied is right. How much of it is up and how much of it is right? This is where we're going to use trig. Really easy. You can see our hypotenuse is my whole force. The up force is related to it. And that makes sense. And it's related to the angle. So let's just think about our simple trig. We have the adjacent side and we have the opposite side. If I want to know, and well, I'm going to try to calculate, I think what I'll do is I'll calculate over here just to allow enough space. So force applied in the upwards direction. How do we get that? Well, it's opposite of 15 degrees. So that must mean I would use sine. So the sine of 15 is equal to the opposite force, so the force applied upwards, divided by 2400. That means the force, I'm running out of space, but I know where I can put this so that you can see it. So that means our force applied upwards is equal to, I'm going to rearrange this. So we multiply by 2400, so it's going to be 2400 times the sine of 15. Okay, so I'm just rearranging that information and bringing it down here. So my upward pull is equal to 621 newtons. Now, I don't need to know the horizontal pull yet, but I will eventually. So why don't we stop and calculate it since we're just used some trig. So this force, well, this is my adjacent side, so it's going to be cosine 15 is equal to force applied right divided by 2400, and the force that's right will be equal to, if you put that in, I'm going to let you rearrange it and put it in your calculator. The rearranging is exactly the same as what I just did. It's going to be equal to 2,318 newtons. Okay, so that's most of the pull is going to move the box forward. A little bit of it's lifting it upwards. Now let's go back to A. What's the normal force? If I'm pulling up with a force equal to 612 newtons, and gravity started out at 2,109 newtons, how much of the force of gravity is left for the normal force to balance? Well, my normal force is going to be equal to what the force of gravity was, minus the amount that I'm pulling up. So we're just figuring out how much is left over to balance, which happens to be equal to 1,488 newtons. So we can put that in. Okay. Now we can figure out the rest. If that's a little bit confusing, don't worry about it. It's going to be okay. I want you to think about balancing forces. So you think about there was one down force, that was gravity. This was my up force that I had to balance, I had to figure out how much force was left for the floor to balance. And then we subtract them to find the difference. So if I'm pulling up, I'm always going to subtract what I pull up with from gravity. But we always have to use trig in order to figure out, well, how much of my pull is actually up, because some of it's pulling forward. It's not all pulling upwards. It's not complicated, but it can be a little bit foggy. If you have trouble with it, or if you have questions, whether you go, hey, I really need some more explanations, I need you to slow down a little bit, please let me know. Okay, let me know, and I don't mind, I'll post an extra video, or I'll give you a little extra time for a lesson and do a pause and recap. All right, so that's A. B, if the coefficient of friction is 0.19, What's the net force? Well, that means we're going to have to find the force of friction in order to find the overall force. So what's the force of friction going to be? It's going to be equal to mu Fn, which is equal to 0.19 times our normal force of 1488 newtons. You will always find that for this course, because we don't have a lot of time, I'll give you extra steps to help you get to the right answers. So now that we have that, the force caused by friction is 283 newtons. Now we need the net force. Now, when we find the net force, we know the vertical forces are balanced. That's what the normal force did. We're just looking at horizontal. And horizontal, we're going to have the force of friction and this force to the right. And we need to balance them out. So we know that 2,000, that's coming from this number, 2,318 newtons was used to pull the box forward. Friction subtracted from that 283 newtons of force, leaving a total of 2,035 newtons available to accelerate the box. So that's my net force. Okay, and then C, what's the acceleration? Well, then we get to some easy stuff. F net equals mass times acceleration. So we know that 2,035 is equal to 215 times our acceleration divided by 215. And you get acceleration is equal to 9.5 meters per second squared. Okay. Probably feels like a really long question. It's not as bad as it looks. Break it down into little pieces. Okay, break it down into small pieces and think about what does each piece represent. All right, we've got one more question I'm going to do. It's similar to this one, so it should help you out. But in this case, we're going to push downwards. So again, I'm going to say, let's read the first part of the question and draw a diagram. And let's analyze the diagram a little bit. A 150 kilogram crate is pushed at a 45-degree angle downward with a force of 750 newtons and accelerates at a velocity of 2.5 meters per second squared. So we've got some information. We need to figure out the rest. So start out with the easy part. The easy part is to draw the diagram. So you've got our crate. Okay. I'm pushing down. And they said it was 45 degrees. The push is 750 newtons. Okay, that's how much I'm pushing down. Let's pause there before we look at this acceleration bit. We're going to leave that till the end. And let's figure out what the normal force is going to be. So we know that the vertical forces need to balance. I know that there's one force pushing down on it already, and that's the force of gravity. That's there whether I'm pushing down or not. It's equal to 150 times 9.81, which happens to be equal to 1472 newtons. But there is another force pushing down, and that's my force pushing down. How do I figure out my force pushing down? Well, this is the side opposite the angle. So again, we're going to use trig. Pop it up here. So we know that this is the opposite side. So it uses sine. So the sine of 45 is equal to the force applied downwards divided by 750, which is my hypotenuse. The force applied downwards is going to be equal to 750 times sine 45, which gives us a force of, I have it written down, 530 newtons. You'll do the same thing for, so that's our force downward. okay? So that's pushing down on the box as well. We'll leave this force till the end. What's the normal force? Well, gravity pushes down. So what's the gravity pushes down plus I'm pushing down. So the normal force has to balance. It's equal to the push down of gravity plus my push down. It has to support both of us. It's only equal to the amount that I'm pushing down, not the total force that I'm pushing with. Adding those two together, we get a normal force. This increases our normal force of 2,002 newtons. That's the balancing force. Because some of this force is already downward. Now, one little trick, we didn't calculate this, the force, the amount of my push that's pushing forward. I'll call it force applied forward. When you have a 45-degree angle, both parts of the triangle will be equal to each other. So if you have one, you have the other. So this is going to be 530 as well. You can test it and put your cosine in and check, but that is a little shortcut you can use. When you have a 45-degree angle, the two legs of your triangle will be the same. So you have both the same measurement in both. B will need this. It says, it should be what is the net force required for this acceleration? It's an easy question. F net equals mass times acceleration, which is equal to 150. We already know that, and the question told us what the acceleration is, times 2.5. The net force that you need to have to make this box move that fast is 375 newtons. C, what's the coefficient of friction between the crate and the floor? Ugh, we need to find friction. If I'm pushing forward, friction's pulling back. Okay? If I need a net force of 375, how much is the force of friction? Well, let's just do a quick analysis. I'm pushing forward with 530. Friction pulls back with how much? Well, the net force is going to be equal to 530 minus the force of friction. Okay, so if I want to know the force of friction, we're going to rearrange our equation a little bit. So we're going to have 375 equals 530 minus the force of friction. Oops, got to throw 0 in there. So the force of friction will be equal to 530 minus 375. Just rearranging it, which leaves us with 155 newtons. So what's the coefficient of friction? The force of friction is equal to mu Fn. Friction is 155. It's equal to coefficient times the normal force of 2,002 newtons. So our coefficient, dividing both sides by 2,002, dividing the coefficient of friction is 0.077. Very, very, very tiny. Obviously, this is a very smooth surface in order to be pushing down that much and still have the box slide. Okay, so that kind of gives us our three answers. Some of these answers are easier than others. The first two should be nice and easy. Part C does require some critical thinking, okay? You won't have a lot of these on an assessment, but you can expect to see one question that will require you to do the critical thinking that would be required, like in C, in order to figure out what's left over for the force to be friction, okay? If you need some more examples of this type, let me know. I will give you a couple in a worksheet so you can use them for some practice. I don't want you to spend hours working on them. I want you to get the big concepts from them. So that's why we only have a couple examples of them. I'm not going to spend 2 weeks on them, which I would do if I was in high school. You might spend a whole 4 classes on them, but you really only have one lesson dealing with this component. Now, some important concepts, some key highlights to remember from this lesson. Friction always depends on two surfaces in contact, always. If there's no contact between surfaces, you will not include the force of friction. Makes sense. It's always dependent on the reaction force perpendicular to the surface. The reaction force, by that we just mean the normal force. The more force there is pushing up on the object from the surface, the greater the reaction force of the normal force, the more friction there will be. The less there is, the less friction there will be. And it always opposes the motion of the object. If you're sliding something up a wall, friction will be down. If you're sliding something down a wall, friction will be up. Okay, so it always opposes the motion of the object. So if you're not sure which direction to draw it, think about what direction is this object moving, and then do the opposite. Friction will always require more force to maintain motion. So if there's friction, you're going to have to use more force to keep motion going. We'll look at that when we look at energy next week. And reducing friction will always reduce the load on a person, an engine, or a motor. That's applying the force to cause motion. And again, I say that now because I want to bring that back up when we talk about work, energy, and power. But that is not for this week. That's a nice, simple lesson for next week.